Hi, welcome to this demonstration class. In this class we are not taking you to the lab, but we will kind of give you an understanding about the pressure sensor, and then how can you use pressure sensor with Arduino as a microcontroller. Okay. So, if I want to use pressure sensor and if I press it, then how can I change this pressure value, or how can I see what is the pressure that I am applying in terms of some digits. So, can I use a Arduino as a controller in between as a interfacing module to measure the change in the pressure at the output signal. So, this is the demonstration class. We have thought a lot after before putting this particular class into this coursework, and it makes a lot of sense, because once you have pressure sensor, how you will be using the signal conditioning module to use the pressure sensor. So, focus on this class, and if you have any question, just you can feel free to ask me. I will just request some other teaching assistant to show it to you how to use pressure sensor with Arduino module as a demo class, right. Till then, you take care. Have any question, please ask me. I will see you in the next class. Bye.
Hi, welcome to the Sensors and Actuators course. Today we will be discussing about a pressure sensor. So, I will be showing demo with the pressure sensor called as BMP180, which is developed by Bosch, and also I will be explaining about the working principle of a pressure sensor. Okay. Professor Hardik must have already discussed with you regarding how a pressure sensor is fabricated, how a diaphragm is fabricated out of silicon and other things. So, now I will be showing a practical example of one pressure sensor like that. So, today we will be discussing about this BMP180 sensor that you can see on this side. Okay. So, this is the pressure sensor that we are going to discuss today. Okay. So, BMP is like many other sensors that are working based on piezoresistivity. So, you must have also heard about piezoresistivity, piezoelectric nature and so on. So, it is basically like if it is a piezoelectric material, then if you apply the pressure, it will generate a potential, while a piezoresistive material will exhibit a change in resistance. So, what a pressure sensor over here will be using is its piezoresistive property. So, you can see here. So, this is the how the construction aspect of a pressure sensor that we are going to use here. Okay. So, you can see here that there are piezoresistors, okay, and in the center there is a diaphragm. Okay. So, a diaphragm, and in the four edges of the diaphragm there are piezoresistors, and the diaphragm over here, this is the side view or a section view. So, you can see there is a piezoresistor here, there will be a piezoresistor here on the both sides, and the thin diaphragm is between it. So, this diaphragm is actually like hanging on these four piezoresistors. Okay. So, okay, that is how the construction of it is. So, this will be a solid region, and by micro machining operation we have got a thin diaphragm, and we have also built piezoresistors on it. Okay. Now, before going further more into this, I will like to tell you about some more things regarding pressure. Okay. So, what is pressure actually? So, you must be aware of force. What is force? Force is like force is what you apply on as objects to move it. So, if I am moving a cart by pushing it, I am applying a force, right. So, this is what force. We know different kind of force: gravitational force, electrostatic force, mechanical force, such many of such stuff are there. And pressure is a concept that is related with force, and it is the pressure is defined as the force applied per unit area, okay, or the pressure is the force applied over an area, and the equation of pressure P is equal to F by A, where F is the force applied and A is the area on which it's acting, and pressure is always acting normal to the surface, and this area is this surface area, and the force acting on it is considered as the normal force acting on it. Okay. So, you can see here. Okay. So, this force over here is a normal force and not inclined force. So, the pressure, if it's an inclined force like what I am going to show now. So, if it is an inclined force, then the normal component will be like this over a theta. If this is F, then this is going to be F cos theta, and then the pressure P acting on this surface will be F cos theta by area. Okay. So, it is the normal component of the force by the area over which it is acting. Okay. So, in SI units, you know SI units. So, okay. In SI units, the unit of pressure is Pascal. Okay. 1 Pascal, and 1 Pascal or 1 PA, that is how we denote it in short form, is equal to 1 Newton per meter square. Okay. So, this is the unit of pressure. Okay. So, we told you that when we apply a force, it acts on an area, and that force per unit area is called as pressure, and it should be normal. The force taken here is the normal force. Okay. So, as I have, even if we apply an inclined force, this is how the force is resolved and pressure is calculated. So, you have an idea about pressure. When we you must have heard of a gas cylinder. Okay. You must have heard of gas cylinders, and there will be prescribed maximum limit for the pressure that can be stored in a gas cylinder, and such stuff are there. Okay. So, we will go into that now. Okay. So, there is something called as barometric pressure. Okay. What is called as barometric pressure? You must have also heard of it as atmospheric pressure also. So, here I have got a diagram. Okay. Here you can see this cuboid over here. Okay. In it's written top of the atmosphere. Okay, over here. So, consider this cuboid, and this is the surface of earth. I am just giving an example. Okay, this is the surface of earth, and consider a cuboid like this, and inside this cuboid there will be what? Air. Okay. This air also have its own density. Water has its density of like 1 gram per centimeter cube, 1 gram per cc, right? And similarly, metal have more density than gases, and so on. So, you must have learned these basics before also. So, consider the atmosphere, it has air. Okay. And I have considered this area of earth, and this much air is over here inside this cuboid. Okay, this is the top of the atmosphere. So, whatever air is there in between the top of the atmosphere to the surface of earth will be causing a weight. Okay, this will have a weight, and in this case we could calculate it as see if this is area A, length A, and this is length B, and say there is a height C, then the volume of air will be A into B into C. Okay, whatever unit, maybe it could be in meter or whatever it is. So, the volume can be ABC. Say I am saying it is in meter cube though. So, we have the volume, and if we multiply this volume V, okay, this volume V into the density of air, I am writing rho is density of air, then what we get is the the weight of air, right? Okay, or mass of air, actually it is the mass of air, and if I multiply it with so this is the mass of air, say m, and if I multiply this mass with acceleration due to gravity, then I get the weight of air. Okay. So, this much weight is equivalent to force, and the Newton the unit of weight is nothing but Newton. So, this much volume of air over here will cause a weight of W air, and this will create a force only, and this force acts on this area A. So, the pressure acting over here P will be is equal to W air, correct, W air by this area. So, this much force is acting here. So, this is a very basic concept, and then we call this pressure as atmospheric pressure. Okay, atmospheric pressure. Okay, so it should be understood that this is not exactly like the density of air is not a constant like I assumed here as rho air. It is not constant, it varies with the altitude. You know that there is different layer heights for atmosphere, so it actually varies. So in the troposphere it will be different, stratosphere it will be different, and it depends on temperature and a lot of parameters. And we have something called as standard atmospheric chart. So, this is not important for the course, but you should understand that there is something called a standard atmospheric chart, which is not just a chart. It has the relation between temperature, density, and a lot of parameters related with atmosphere, its density, a lot of things. It's actually a good thing to know. It's like very fascinating thing. You can actually look into that anytime. Okay, so even though I told this as simple as this, it's not like this. So it does, this pressure actually is not like this. It's actually a sum up of the various densities and other things. So at different layers we will have different densities, different weights, all sum up to finally this. So we can say okay, the total weight sigma of whatever weight over the area is the atmospheric pressure. And at sea level it's being calculated that the standard atmospheric pressure at sea level at a temperature of 25 degrees Celsius. It is very important to note that this pressure, that is 101,325 kilopascal or is equal to 101,325 Pascal, is the same, just the kilopascal. So this value of is called as standard atmospheric pressure, and it is at 25 degrees Celsius. Okay, it's at 25 degrees Celsius. If temperature changes, pressure changes, so it's very important. Okay, so this is the standard atmospheric pressure. So we also have given it as a term or a unit as 1 atmosphere, ATM, is equal to 101,325 Pascal. Okay, this is a standard value. Remember this always. 1 atmosphere is equal to 101,325 Pascal. Okay, and this is called as 1 atmospheric pressure. So if you are going near a sea, and then the pressure of air acting on you is equal to 1 atmosphere and is equal to 101,325 Pascal. Okay, so this is also called as barometric pressure. Okay, this is called as barometric pressure. So it's right. It's also known as atmospheric pressure. This is the pressure applied to any object that is in an atmosphere, example on Earth. Okay. So barometric pressure is measured using an instrument known as barometer. This must be, we all must have studied this during our small classes itself, that okay, what is the instrument used to measure pressure? It's barometer. So this is also a sensor. Okay. So we are going to see how we are going to use the BMP 180 that we discussed earlier as a to be used as a barometer. How it, barometer is mechanical in nature, the conventional one, but this one is an electronic barometer that we are going to do. Okay, so this is the one thing. Why I said about barometric pressure, I will tell you. So there is something something else called as manometric pressure also. Okay, so consider this. This is a cylinder. Okay, this is a closed cylinder. Okay, and inside it there is air. Okay, air is there, and air is stored as a pressure. Okay, air is stored as a pressure P, and the volume of the container is fixed, say volume V. Okay, so okay, there is P and V. I am just naming it as, okay, let it be P, and see this cylinder is on the surface of Earth. So there will be atmospheric pressure acting on it, right? Atmospheric pressure will be acting on it, correct? So there is a term like anyway there will be a pressure of around 1 atmosphere always on the surface of earth, correct? So we like, so it's already like 1 atmosphere is added to any pressure measurement we do. So we came up with a new term called as manometric pressure, okay, so that we can get a value that starts from 0. So it's nothing but it's the only pressure that is built up inside the system. So it is also known as a gauge pressure. It's known as a gauge pressure. Manometric pressure is also known as a gauge pressure. This is the internal pressure of the system. This is the internal pressure of the system and does not include barometric pressure. So it's like a cylinder, this cylinder has a pressure inside is equal to 5 atmosphere. 5 atmosphere is nothing but 5 into 1 atmosphere or 5 into 101,325 Pascal. That much pressure, that's like higher pressure, 5 times the atmospheric pressure is inside this. Then the gauge pressure is equal to 5 atmosphere. P gauge is, or P manometric is equal to 5 atmosphere, but the real pressure or the absolute pressure that we will discuss now is equal to 6 atmosphere, because this 5 atmospheric pressure or the gauge pressure is devoid of the atmospheric pressure or the barometric pressure, okay. So this is like a new reference that is devoid of the external pressure. Anyway we know that there is an external pressure equivalent to P atmosphere. So we will say that, why we have to say again. So keeping the atmospheric pressure as the reference point, we will count from that. So okay, 2 gauge pressure of 2, P gauge of 2 atmosphere means nothing but, okay, 1 atmospheric 2 atmospheric pressure greater than the normal atmospheric pressure, okay, that's it. So that is what a gauge pressure or manometric pressure is. So very important to note that this value can be negative, okay, this value can be negative because see the atmospheric pressure that we discussed as 1 atmosphere, okay, 1 atmosphere, we know that when we create a vacuum the pressure decreases. When we create vacuum, pressure decreases, correct, pressure decreases. So the pressure of the inside the cylinder, if we create vacuum, will decrease beyond 1 atmosphere, correct. So since 1 atmosphere was considered as the 0 for a gauge pressure calculation, this value becomes negative now. This P gauge will be negative. So the manometric pressure can be negative, okay, while the atmospheric pressure cannot be negative, okay. And then we have the absolute pressure. So it's nothing but the total amount of pressure including both manometric and barometric pressure. So there is an absolute pressure that is equivalent to sum of barometric and manometric pressure, and which will always be positive, okay, which will always be positive because manometric pressure can reduce up to say if we create a lot of vacuum, excellent vacuum, then will like be negative, but it doesn't go below barometric pressure a lot. So the absolute pressure will always be positive, okay. So this is the concept that you need to know before we go into details of a pressure sensor, okay. And one more thing that I think you should know is some basics of thermodynamics that we must have known before, okay. So this is the it is the Charles law actually. So Charles law is nothing but volume is directly proportional to the temperature, okay, volume is directly proportional to the temperature. So when the temperature increases, volume also increases. When temperature increases, volume increases, or temperature decreases, volume decreases. This case is very tricky actually. So this is in case of a isolated system actually. Isolated system means no energy is lost, no energy or matter is lost outside. Then if we increase the temperature, volume will increase for a isolated system. Okay. Then when we increase the temperature, volume will also increase. Okay. When we decrease the temperature, volume will decrease. And then there is Boyle's law. Okay. That says that pressure P is inversely proportional to the volume, or PV is a constant. Okay, constant A, or like that. So if pressure increases, volume decreases. A simple example is, consider this is a cylinder and I am keeping a piston like in the SI engines and all. Okay. So if I apply pressure here, what happens is, pressure inside, or the air is inside this cylinder. When I apply the pressure here, the cylinder is the piston is going to come down and the volume decreases. Correct, volume decreases. When volume decreases, what happens? Pressure increases. You know this example. This example we will be showing you today. That's why I am just telling you this basic example so that you will have the idea. And one more important thing that you have to remember is, when we use these equations, we should remember that volume can be in meter cube or any other SI unit, doesn't matter, but temperature should be in Kelvin. Kelvin is the SI unit of, everything should be in a standard unit. Okay, Kelvin is the SI unit of temperature. So you know that, yeah, 0 degree Celsius is equal to 273 Kelvin, right? Yeah. So temperature should be in Kelvin, and pressure should be in some standard unit, and this standard unit should be in absolute pressure. Okay, we can use Pascal or atmosphere, okay, or bar. These are all units of pressure only, but we should use the absolute pressure, not the gauge pressure, absolute pressure in the calculation. For example, I would say, according to this relation, okay, PV is a constant, we can say that P1 V1 equal to P2 V2, right? So you understand that, right? Yeah. So initial pressure and initial volume, the product of those two will be equal to P2 V2 will be is equal to a constant A, correct? That's what according to Boyle's law happens. So initially, if the atmospheric pressure was 5 atmosphere and volume was 1 meter cube, then if I increase the pressure to say 10 atmospheric absolute pressure, then the volume will decrease actually to how much? To 0.5, so that this constant will remain same. Okay, so this is how Boyle's law works. Okay, and then we also need not mention much, but ideal gas law is there, that is PV is equal to nRT, where N is the number of moles, R is the universal gas constant, which is equal to 8.314 joule per mole Kelvin, and T is the temperature in Kelvin. Remember, always use the SI unit, and the SI units of pressure should also be in absolute pressure. Very important thing, always remember this. Okay, now we will be going back to the pressure sensor. Okay, so this is the BMP pressure sensor that we are going to demonstrate. Okay, now I am going to apply some force here, and external pressure will be acting over here. Okay, so what happens is, due to this external pressure that is going to act here like this, what happens is a tensile stress is going to be produced. Stress are of two types, not two types, more than two types are there, but I could simply say that pressure can be tensile, stress can be tensile. Stress and pressure are almost the same, but we are not mentioning that, you will be confused. So there is something known as tensile stress. For example, tensile stress is the stress developed when you pull a block from this side and this side, so it will stretch, right, like a rubber band you stretch. So that's the tensile force. And you take a sponge, okay, you keep it somewhere and you apply force, then it compresses, right, and it reduces the size. This is called as compressive force. Okay, and the stress is called as compressive stress or compression stress. Okay, tensile stress, compression, that's the stress that is going to happen. So here tensile stress will be produced due to this external pressure over here, okay, on the thin diaphragm. So the thin diaphragm will deform, and when it deforms or it comes down, what happens is this, since this piezoresistor doesn't stretch much, there will be tensile stress, and this will cause the change in resistance, and that is why we are saying that this is piezoresistive sensor. Okay, so the output is actually a resistance change. So there are 4 piezoresistors here, and we will be using an so we will be using a signal conditioning unit to get this output. Okay, so this is how a pressure sensor works. And this BMP 180, okay, it has a detection range of 300 to 1100 hectopascal, that is equal to 300 into 10 power 2 Pascal. Hectopascal is equal to 10 power 2 Pascal. Okay, 10 power 2 Pascal. So 300 into 10 power 2 Pascal to 1100 into 10 power 2 Pascal. This is the measurement range of this pressure sensor. Okay, so and it uses something else called as I2C interface with Arduino. When I am going to show the example, I will tell you. So this is a different mode of communication. This is also serial mode of communication only, but it uses 2 wires. Okay, for the 2 wires for communication. So it's like a serial communication only, but with very high speed. So it's an I2C communication. We won't be going too much into it. Okay, and yeah, so this is the main thing. Okay, cool. Then why we use this is, I told you initially about the standard atmospheric chart, right? Yeah, we talked about standard atmospheric chart where the pressure variation as well as density variation, everything will be plotted. It's like a graph like this. Okay, various values will be shown. So it's like okay, so I will be plotting, say, pressure here, density here, temperature here on the y axis, in different y axis, and it will be plotting altitude h on this thing, and it will be like, okay, the temperature the first increases, then it drop, it stays similar like this, and the pressure actually increases, then drops, something like that. It's not exactly like this, but something like this. Why we develop this standard atmospheric chart is for mainly because we need to do fly aircrafts and rockets and everything. Since all these things fly in the air, we need to exactly know the pressure variation so that we could adjust the thrust and everything in the aircraft. So these pressure sensors are widely used in aircraft and other things to measure the pressure outside and do the calculation as well as, and since the atmospheric pressure at that height will be more or less the constant, they even use a pressure sensor to calculate the altitude. Okay, so they will measure pressure and predict the altitude. So a lot of applications are there for pressure sensors. So why it is written as enhancement of GPS navigation is that when we get the pressure value, we will be exactly able to know the height, range and all. Okay, so slope detection, everything. Then we can do weather forecast. Okay, so when temperature changes, there will be change in pressure, so we can use it for weather forecast. Okay, and vertical velocity indication. So this is for the aircrafts, they have a instrument inside it. Okay, so it's something like this with a it's called as a vertical velocity indicator and all. So what happens is, when it moves fast, based on the pressure variation, it will show the velocity at which it is moving up and down. Okay, and leak detection. If we keep a pressure sensor inside a cylinder, if it's leaking, the pressure will drop gradually and we will be able to know that there is leak. And for volume measurement, as I said, PV is a constant. Okay, if pressure decreases, we know that the volume of air also okay, if pressure decreases, then the volume actually increase. Okay, so we can do a lot of things like this. Okay, so this is about the pressure sensor. Now we will switch to the showing how it happens in Arduino. So you can see here I have connected the BMP pressure sensor to the Arduino Duo. Okay, you can see here, and there are 4 cables that's coming from the BMP pressure sensor. It's the same that the pressure sensor is almost the same thing that I showed you in the presentation. So you have here the casing with the thin diaphragm inside, and 4 cables come out of this, out of which one is 5 volt, one is ground, and then there is SDA and SCL. Okay, these are the 2 connections that we use for I2C communication. Okay, you can see here I have already connected it. Okay, now we will move on to the Arduino programming. Okay, so here it's the same thing that we always used to do. Okay, you can see that in the tools I have added a new library. Okay, BMP 180. Okay, I click manage libraries, inside which you can search BMP 180. So you can add it. Otherwise, it's a bit of tricky to code the I2C communication by yourself, but so it's better to use it directly if you are not very experienced. So I have already installed it. BMP 085 or BMP 180 library is available here. So you can just install it. I have already installed it. Okay. Now you can see that from the file examples I have selected this code. Okay, Adafruit BMP library here. This is the code over here, and there is a header that we have to call for wire.h that is used for the I2C communication. So wire.h is popularly used for communication protocols, and it has a lot of functions inside it, and we also added the Adafruit BMP 085 library into it. Okay. Then we already, since we have connected the VCC of the BMP 180 sensor, here it's 085, but in our case it is 180. It doesn't matter anyway, it's a command. Okay, and it should work at 3.3 volt. Its working level is 3.3 volt and not 5 volt. So you should remember that. Okay, connect the ground to ground of the Arduino, and the SCL pin from the SCL or the clock pin from the sensor to the clock on the Arduino. And in case since we have used the Arduino Duo, okay, the SCL pin is pin number 21, digital 21, and the other pin is pin number 20. SDA pin in Duo is pin number 20. Okay, so we have connected it like this. Then there is a bit of code over here. So it's BMP.begin. It's like the communication we have used before also, the serial.begin. Similarly, we have used BMP.begin here. That means a serial communication is starting between BMP sensor and the Arduino board. Okay, then inside the void loop we are using a set of functions like BMP.read temperature and other things, and we are printing it on the serial monitor. Why we are doing this is that we can easily use the sensor without much coding, so that you can easily understand. Okay. So what it will show is temperature. There will be temperature feedback from the pressure sensor. So this pressure sensor also have temperature measurement inside it. So okay, so we can read the temperature. Then also we can read the pressure. Okay, and based on the assumption that standard barometric pressure is 101325 millibar or 101325 Pascal, we can calculate altitude. As I already said, aircrafts use this method to of like the measurement of pressure will be converted to the measurement of altitude. Okay, so you can see that altitude can be measured, pressure at sea level can be measured, and a lot of things are possible. Okay, the real altitude, everything. So I am just going to select the board as Arduino Duo when programming port. It's already selected, and the COM port, and I am going to upload. Okay, verifying the code now. Okay, and I am uploading the sketch now. So this code will be uploaded into the pressure sensor now. Okay, now if I select the serial monitor after uploading, yeah, the blue progress bar is here. It's just getting uploaded only. Okay, it's done uploading. Now if I am selecting this, see, I can see the temperature and other things. Okay, it's showing the temperature as 23.5 degrees Celsius. Okay, 23.5 degrees Celsius, and the pressure as 95 954, okay, 90539 Pascal, okay, and an altitude of 939 meters, okay. So I am sitting in Bangalore right now. So Bangalore is at an elevation of around, as according to the sensor, it is at 939 meters. You can actually check how high is Bangalore from the sea level to cross verify it. I do not know exactly, but yeah, let's see. And also you can see that the pressure is, this pressure is the absolute pressure, right, and this absolute pressure is less than the atmospheric pressure. It's because at a higher altitude this pressure actually decreases, the atmospheric pressure actually decreases. So it is below 101325 Pascal. And if we measure the gauge pressure using a gauge pressure sensor over here, then what happens is we will get a negative gauge pressure, right. We will get a negative gauge pressure because the gauge pressure is equal to the absolute pressure minus atmospheric pressure or barometric pressure. So which is equal to this pressure 90538 Pascal minus 101325 Pascal, which will give you a negative gauge value, okay. So this is how we connected between absolute pressure and gauge pressure, okay. You should understand that, okay. And similarly you must also remember the Charles equation, Boyle's equation and everything, okay. Now that you have seen this, I will show you the variation in the pressure also. So I will put the gas sensor inside inside a balloon, okay, inside this balloon over here, okay, and I will inflate the balloon and seal it, okay. So when I do that, what happens is the volume of the air within the balloon will be like constant, right, because once I seal it off, the air cannot go out, correct, air cannot go out. So if I compress the balloon, what happens is the pressure will build up according to which equation, the equation over here that we have seen. Which one is that? See, okay, it's the Boyle's law. According to the Boyle's law, what happens is when we decrease the volume, pressure will increase, okay. So according to the Boyle's law, what happens is if we compress the balloon, the pressure will go up, and we will see that on the serial monitor, okay. Now we will do that once. So I have put the pressure sensor inside the balloon, okay. So it's like this. Now you can see that pressure sensor is within this, and I have connected everything, okay. So theoretically what should happen is when I compress this, the volume decreases and the pressure should increase. But since this is a balloon, it can deform, okay, it can deform. So the pressure change won't be so visible, but still you can see a pressure change in the serial monitor, okay. Now you just look at the serial monitor now. So the value of pressure is around 92,000 Pascal, okay, 92,600 or 680 Pascal. So if I am going to compress it now, okay, compress the balloon. See, I am going to compress the balloon, and you can see that the pressure has increased to 93,347. So there is a increase of pressure of around 500 Pascal, correct. I am leaving the hand now, again back to normal. See, the pressure has even dropped back to the normal 92,600. Again I am compressing it. See, the pressure has increased, correct. So you can see that it is calculating the pressure accordingly. But you can see also something else, that when I increase the pressure, okay, you can see the values that the altitude has decreased. So it is the calculation actually an error, because when the pressure increases, accordingly the altitude should also decrease, correct. Yeah. So this is how the BMP 180 pressure sensor works. Okay, I hope you understood how the BMP 180 pressure sensor works, and I think the concept is clear. You can also know how microfabricated sensors using thin as well as thick film sensors are widely used, okay. So that's it. Thank you.